Hi, in this video I'm gonna show you how to use the Anova table to compare the sum of squares that I showed you in the previous videos. Remember the two sources of variation that we have in our models? We have a source of variation that comes from the regression model. What is the regression model? The regression model is the model that we establish between x and y. For example, let me show you on the Armand's. Remember the restaurant problem, the Armand's pizza parlor problem. So this is our equation. This is our regression model. This is the regression model I'm talking about. The regression model is when you establish a relationship between a dependent variable y, in this case sales, as a function of another variable which is called independent variable in the model, and in this case is the student population. So this is our model. We are modeling the sales y, how much sales vary based on the student population. So this is what the regression is. So there is a source of variation that comes from this model that we created to explain the sales, and there is another source of variation which is called error, because in our attempt to understand sales, to explain sales, we commit mistakes because it's impossible to predict everything precisely. So there's no crystal ball, and then we have some errors. So there's two sources of errors in each regression model. And remember that I used this applet to explain to you the relationship between these two variables, the student population and sales. Here is the model. This model doesn't explain anything because sales doesn't vary. Sales is constant. So I can vary the student population. I'm increasing student population, but sales doesn't go up, doesn't go down. So this model doesn't explain anything. Look, the R-square. R-square is 0. So this using this model or modeling sales using student population according to this linear model here doesn't explain anything. Remember, R-squared, the coefficient of determination, is 0. So we have a source of error here. So all these big red lines are the errors from the actual observations, the actual data, and the prediction in this linear model. Remember that if we move that to make it closer and closer and closer to the actual data, we are reducing the errors. We are decreasing the amount of mistaking we're committing, and we are increasing the blue lines, which is our assertiveness. Okay, look how the R-square now is almost 90%. So 90% of the variability in sales is explained by variability in student population. And this bar, blue and red bar, is for you to help you understand the proportion of error in red and proportion of regression variation in blue. So the higher the proportion of regression variation, the more assertive our model is, which is shown by the coefficient of determination. So they're all tied together. The sum of squares and the coefficient of determination and now the Anova table are together. So the Anova table is a different way of looking to these same sources of variation. Okay, here we have source of variation, regression and error, blue and red. And then if we sum this, here we're going to have numbers. If we sum them, we have the total sum of squares. Okay, then we have the degrees of freedom. The degrees of freedom for the regression is the number of independent variables. We have only one independent variable, so the degrees of freedom is 1. The degrees of freedom for error is the sample size minus 2, and the degrees of freedom for total is n minus 1. Then if we divide the sum of square by 1, if we divide this number by this number, we get the mean square regression. Okay. And if we divide the sum of square error by the degrees of freedom, we get the mean square error. Okay, and then if we divide this number by this number, we get the F statistic. Remember, the F statistic is another statistic that we have. And if we have the F statistic, we can find the probability value. Here are the formulas to find the probability values, okay? To use the p-value approach and to use the F-critical approach. It's very similar to what you did in chapter 13, so I'm not going to spend too much time in here, okay? But then what this is testing is how much variability we have from our regression over our error. If we have more regression variation than error variation, then our model is able to explain our dependent variable, in this case sales. Okay, let's take a look at the Armand's solution. Remember, when we have the raw data, like in here, we can use the data analysis tool, and then we get these results. These are the coefficient of determination. This is the coefficient of determination. This is the Anova table. Look, the Anova table. Okay, and then let's go over that very in detail to understand that. So remember the degrees of freedom. I told you only one independent variable, which is student population. We have 11 observations, 11 cases, 11 restaurants. The degrees of freedom, 11 minus 2 is equal 9. 11 minus 1 equal 10. These are the degrees of freedom that we have here. Degrees of freedom. 11 minus 2 equal 9. 11 minus 1 equal 10. This sum of squares are given, they are computed by Excel. Okay? And then if you divide this number by this number, you get the mean square. If you divide 170 by the degrees of freedom, you get 18.88. If you divide this number by this number, let's do it here. If you divide this number by this number, you get the same number you have in the F. And then the significance is the p-value. The p-value is equal F distribution RT, this formula right here, and this is the F. Degrees of freedom 1 is here, the degrees of freedom 2 is here, and then you get the same number. So this is where these numbers are coming from in the Anova table. Okay, so this is how you get the Anova table, and this is what they mean if you use the raw data. But also we can find some problems that have only the Anova table, like problems we had in chapter 13. Let's take a look at the homework so you can see how these problems can come to you. And so if you go to the homework assignment and let's wait for it to show up on screen. Okay, let's start the assignment now. And let me show you one problem here. I think this one is no. Okay, come on. Here you go. Okay, so you have an Excel file. You have production volume and total cost. You download the file, you run the analysis, and you get the answers from the Anova table. You fill all them here, and you find your conclusion. Okay. So this is how you get the answers for the Anova table. This is another kind of problem that you can find. Like sometimes you can have only parts of the data in the table, and then you have to fill out the table with the information. Okay. And then this is how you're going to use, or you can download the data. In this case, download the data, run the regression analysis in the data analysis tool, and then you have the answer. You have to come up with the B0 and B1, and then I'm going to talk about these t values in a minute. But okay, this is how we're going to use. Let me go back to one of the problems so I can show you what you have to do. Again, you have the data, you have two variables. One is dependent, another one is the independent, and you have to come up with the equation, finding the B0 and B1 using the data analysis tool, finding the R square, which is the coefficient of determination, and then coming up with prediction and so on, okay, and interpreting. So this is how you have an Anova table involved in regression, and I'm going to stop here and talk about test of significance in the next video.